My name is Mokshetri and this is my video for assignment 4 in COM 3132. In this assignment I had to take everything we learned this semester and use it to build a convolutional neural network. Here I have imported the libraries we needed for this assignment. Now I used CFR10 dataset which is 60,000 smaller color images across 10 classes like airplane, cat, dog, ship and truck. The first thing I do is data preparation. I load CFAR from Keras which already comes split into 50,000 training images and 10,000 images. I normalize the pixel value from 0 to 255, the range 0 to 1 because neural network trained better with small similar scaled inputs than I one hot encode the levels because I have 10 classes and I use softmax at the output. Next is train validation test suite. CIFAR10 already gives me a test set of 10,000 images and that I keep completely aside until the very end. From 50,000 training images, I take the first 5,000 validation set, the remaining 45,000 stays as the training set. The validation set is what I use during training to see if a model is overfitting. The test set is only used at the end to get honest final accuracy. So, model 1 for my experiment, I built a very big CNN on purpose to show over parameterization. It has 4 convolutional layers with 64 and 128 filters, then 2 huge dense layers, one with 1024 neuron and one with 512. That's way more capacity than CIFAR10 actually needs, so the model can just memorize the training set. I trained for 30 approaches with regularization at all. When you look at the graphs, you can clearly see the overfitting. Here is the graph. You can see on the left of in the graph on the left the training accuracy in blue keeps going up, but the validation accuracy in red flattens out pretty early. The gaps between them gets bigger and bigger. That gap is overfitting. On the right the training loss keeps dropping, but the validation loss actually starts going back up, which is the clearest sign that the model is memorizing the training data instead of learning general patterns. Now let's go to model 2. My first fix is regularization. I added two things at the same architecture: L2 regularization and dropout. L2 adds a penalty on large weights so the network is pushed out towards smaller, simpler weights that generalize better. Dropout randomly turns off percentage of neurons during training, 25% after the conf blocks and 50% before the final year, so the network can depend on any single neuron and basically has learned reduced more robust feature. After training the graphs, this looks much healthier. Now here is the experiment 2 graph. The gap between training and validation accuracy is much smaller than experiment 1. The training accuracy is a bit lower, which makes sense because I am penalizing the model for being too confident. If the validation accuracy is higher and the validation log stays flat or it keeps going down instead of shooting up. Experiment 3. My second fix is data augmentation. Instead of changing the model, this technique changes the data. I added a keras layer at the top of the model that for for every training image randomly flips it horizontally, rotates it and zoom in a bit and shifts it around. You can see how the same image becomes slightly different every time the model see it. So effectively training set is infinite. The forces the network to learn features that are actually about the object, not about its exact position or orientation. I combined data augmentation with L2 and dropout from experiment 2, and I also added early stopping with the patient of 6 epochs so training stops automatically if the validation loss stops improving. This is the best behaved. So here's the experiment 3 graph. This is the best behaved model. The training and validation curves are really close to each other, so almost no overfitting, and the validation accuracy is highest of all three experimentation. And the final comparison that I plotted the validation accuracy of all three experiments on the same graph. Here is the comparison chart. You can clearly see that experiment 1 pretty lowest and experiment 2 is better and experiment 3 with the data augmentation is the best. Then I evaluated all three models on the test set data none of them had ever seen. So here is the printed test accuracy number. The recommended model is a winner on the test set, which proves that fixing overfitting actually gave me a model that works better on new images, not just on training data. Number of epochs and summary. The last topic is number of epochs. The right number of epochs isn't the biggest number possible. It's the epoch where the validation loss is the lowest. After that, training longer just makes the model overfit. In experiment 1, the best epoch was pretty early, around 10 to 15, and everything after that was wasted. In experiment 3, I didn't have to guess because the early stopping callback automatically picks the best epoch based on validation loss. To summarize, I showed that a big CNN with no regularization overfits CFAR 10 quickly. Adding L2 plus dropout reduced the overfitting. Adding data augmentation on top of that reduced it even more and gave me the best test accuracy. And choosing the right number of epochs switching validation loss is what keeps the training honest. Thank you for watching.